Cool. All right. So that will bring us to parameter inference. Is that right? Yes. Okay. So I've called it parameter inference because I think that's kind of what the curriculum's going through. I'm really going to try to walk you through maximum likelihood estimation of like how it's derived, because I think the curriculum kind of can be a little, it can be a little obtuse in the sense of like what's going on. So I'm going to walk you guys through the reasoning behind it, okay, and why you're able to do this part. So I'm actually going to hide these parts so you guys don't have to be distracted by all this math, right? So the first thing basically is that we have something called the maximum likelihood estimation, which, trust me, we will talk again later, especially in the next module. But note that MLE basically is saying what is likely happening based on our information. So there is a limitation to this. Is that basically it's like if we've never seen rare events happen, we don't know rare events exist. So MLE kind of like, I think the curriculum kind of talks about this a little bit, but it's kind of like trying to figure out how do you figure out if a coin is actually fair? Well, one way is to literally measure out every single detail of the coin like physically and figure it out. Or if you're a statistician or closer to like what a data science is, you flip the damn coin. You flip it and just see what happens, right? And if you keep flipping it, eventually you hope to see if it lands generally 50-50, you probably know it's a fair coin, right? But what might be an issue with this trying to figure out if a coin is fair? Like if I flip it 5 times, or let's say 4 times, you know, what might be an issue of seeing if that's actually fair by just flipping it 4 times? So I think you guys, so if I flip a coin 4 times and I get heads each time, does that mean the coin is like a trick coin?
Not necessarily.
Exactly. And that's like, maybe it is like only lands on head or at least heads most of the time, but you can't know for sure because there is a chance, you know, that it could land on heads or heads 4 times. You can think of that as 1 over what, 16? 1 over 16 times, right? If you had 16 people in the room and they all flip the coin 4 times, approximately on average, 1 out of those 16 people will have their coin land on heads all 4 times. So the problem with maximum likelihood is that you have to do it you're only as good as the information you got from the data. So what you can do, though, the more you do it, the more often you'll actually be able to decide. Like, for example, if I flip a coin 1,000 times, and each time it lands on heads, then you probably say, yeah, that coin's kind of fishy. That's something's wrong with that coin. And that's the power of maximum likelihood estimation, but also it's kind of like its weakness is that you have to essentially, you're only as good as the data that you're given. So this is especially true for like rare events. If you have something that's really rare, it might not ever happen or happen only once out of like all the number of times just because it's super rare, which won't give you a good picture of that. If you do more more experiments each flip, then you're more likely to approach the actual probability of that system. Okay, but I just wanted to point that out for what the limitations for MLE is. The curriculum talks about this Iid assumption, which basically comes down to something called it's independent and identically distributed. And basically those are kind of like similar stuff, but they're slightly different. So independence, hopefully you kind of understand what independence is. Like if I flip a coin, me flipping the coin later on or a different coin, it's not going to affect what's going to happen to the coin. That's not always true for every system. Like you can imagine if the coin really hard and it bends the coin over time, maybe each flip actually does affect what the next thing's happening. So like independence doesn't always hold, but this is an assumption we use for our next derivation. And then identically distributed. So this basically says that each event has the same parameters, and this is kind of similar to independence, but not quite. It basically just means that like the probability doesn't change over time or over each experiment. So you don't have to worry about the coin being affected because it's the same coin and essentially the same environment. But if let's say there's like wind, you know, in certain flips versus no wind, that could affect the probability of the coin flip itself. That's what we want to avoid. But basically that every time you do this event, or do this experiment and have an event, it has the same parameters, meaning the same kind of like things that affect it. So the probability doesn't change over time. So essentially what this comes down to like this Iid assumption is summed up in this mathematical equation. And this mathematical equation, I don't know if you guys have seen this before, but basically it's a capital pi. So like you guys know like the Greek symbol pi. It's kind of like a summation, but instead of a summation, like, you know, with our capital sigma that looks like an E, this is essentially our saying it's multiplied each time, which makes sense. Probability is being multiplied each time. And basically we start off with, you know, the first probability of the first event, okay, up to n events. So if I had like 10, capital N would equal 10. And basically this is saying, okay, the probability of each time this happens, because remember probability could change, for each event, and these are all the parameters, this theta is basically representing the parameters of that flip or whatever event happens. This is basically saying, all right, whatever the probability is for this certain event happening with these certain parameters. Well, if the parameters never change, and the probability doesn't change over time, right? Then that means that simplifies this Iid assumption, simplifies just the probability of this event that happens, so you get different events that happen, have all the same parameters, like given such that parameter. Then you can think of like the parameter being like for a coin flip, like maybe the way someone flips it, that could be a parameter. So the same person flips it the same way every single time, that's their theta. So this is like given that these parameters, so person A flipping it versus person B flipping it, or there's wind or whatnot, or it's a different coin. So that's what the summarizing goes to, okay? And that's just giving all the probabilities on there, okay? So cool. That's some mathanese for you guys to kind of just understand how this works. Okay, cool. Any questions on this guy or the Iid assumption? Okay. And again, this comes in the curriculum, but I just wanted to really point this out. Okay, so this is where the curriculum actually goes through trying to find this theta MLE, okay? And so I'm gonna walk you through this part because I think this can be kind of confusing. So the idea here is that we're trying to find this theta MLE, basically the maximum likelihood parameter. Basically, like what are the parameters that describe the most likely outcome, okay? And by most likely outcome, it means the thing that we saw the most often, right? So if we flip the coin, and if we flip the coin multiple times, you know, and it has a certain amount of data distribution, we would say, okay, this is the likelihood of going on here. And we want to see what's the maximum likelihood, okay? So the way we find this is essentially we're trying to find we're using a function f of theta, which is really this thing right here. That's what this is. F of theta is literally this probability here. Basically all these probabilities of different events happening. Okay, so like you imagine flipping one coin, 2 coins, 3, we'll flip it 4 times. If I flip it 10 times, this n would be 10, and this probability would basically be based on what would the parameters were each time. But essentially we have this function, and the goal is basically to find a critical point and test for the maximum. So the way we find this is basically we would have this function f of theta, and essentially we're just finding the derivative of f with respect to theta when that equals 0. And so I know we talked about this a little bit, but I just kind of quickly review where this is coming from, is that the reason why we're looking for the first derivative for that function f is equal to 0 is that if we have a function like this, let's say maximum is like this, and then it goes like this, I'll just kind of, I don't know, I'll just go like that, something like that. So if we're trying to find a maximum, what's happening here is like, well, okay, right here, the slope is positive, right? And right here, the slope is negative. Okay, which is basically describing a positive maximum. Well, that means the slope right here at some point at the maximum actually hits 0. So the slope is equal to 0. But remember, our derivative just basically describes the slope at any instant point. So essentially what we're trying to do here is say with the function f, where does it hit 0? So that would actually give us the point of saying, hey, that's what we call our critical point. Basically, if it's a maximum or not. However, if you notice down here, this is also a critical point because the derivative here is 0. But of course, we don't want this point. Hopefully that makes it pretty obvious. It's not the maximum, it's the minimum. So the problem is the critical points actually find either a maximum or minimum. There's a third option called an inflection point. I don't know if you guys recall that back from like calculus class, is that, for example, if you have like a cubic function like this, at this point right here, there's at some point here that the derivative hits 0. So that would be like an inflection point that would exist And so that could also be a critical point. So what happens, like, okay, cool, we found a critical point, or we found potential or other critical points, which could potentially be the maximum, but it could be a minimum, could be an inflection. So what we do here is basically take the second derivative of that function and plug in whatever value we found for that critical value and just see, is that greater than 0? Basically, if you want to see if it's a maximum or minimum. I actually think this is incorrect to find the maximum. It should be less than 0. It shouldn't be greater than 0. So that's a little typo that I had. But basically, you just want to test, hey, is it a maximum or is it a minimum or an inflection point? If it's an inflection point, you actually see this equal to 0. This is also, if you remember back in calculus, concave up, concave down. So just kind of putting this in perspective, that's essentially what we're trying to do to find the MLE. And whatever that sigma c, or not sigma, sorry, theta c, whatever this value, if whatever maximum, that is the maximum likelihood value. And basically that's what this is right here. We're trying to find this value. So there's a trick to doing this though, however, because this function is kind of tough to do. It's basically a bunch of probabilities, like probability of theta versus probability of theta minus 1, or 1 minus theta, probability of like theta again, like because we flipped it another time, it landed heads. Like curriculum talks about this more. Basically, you have this weird, funky function that it's just like a lot of work. Like it's just like, okay, this function is really hard to actually take a derivative of. So we cheat basically. So we say, all right, kind of like we're doing a log transform. And you'll notice this in data scientists and mathematicians. We love doing log transforms. So right here, that's essentially what we're doing. We say, okay, well, if we take the log of it first, it turns out our function will look different, right? So if we took like the log of this function, it might look something, I'm just gonna make this up. Like I'm gonna say like, oh, it's like something like this, like that. But it's kind of squished over or whatever. But what's interesting is that because of the log, I think the curriculum actually talks about this, it's a monotonically increasing function, which is a bunch of math stuff basically saying that if the value goes up, the log value will also go up. So what's nice about that is that we can actually find the maximum value, is that even though the actual like height of that will be different, the point at this occurring will actually occur at the same point as here. And that's not usually necessarily like super useful, but since all we care about is like, where does this occur? Basically, this is our theta. Like, where is our theta MXE, our MLE? Is that's the same point here. So what we do is we take the derivative of this probabilities being multiplied together. But if you remember from so like think about like this long thing right here. If I did the derivative with respect to theta, that would just be a huge mess because I would have to do the chain rule. I'd have to consider all those parts in there. It'd be a huge mess in order to do the derivative. But if I do the derivative this way, of like log of these things multiplied together, well, if I do the log of this whole thing, that ends up just being simply the probability, well, log probability, but like the log of p of theta plus the log of p of 1 minus theta, and so on. So essentially, instead of having them multiplied together, we have them all added up together. But taking a derivative with things being multiplied together are a lot easier than it being, taking the derivative of things being added up together is a lot easier than taking the derivative of them all squished up, multiplied together, because we essentially just have to take a derivative of just this guy by itself and then just this guy by itself versus trying to combine them all together with the chain rule. Okay, so this is kind of, yeah, so the product rule, I should say. Or not product rule, yeah, whatever. Basically, the derivatives is a little lot easier. So what's cool about this is that this actually ends up being really easy for us to deal with because the derivative of a log is essentially just 1 over whatever the function is, which in this case actually ends up just being theta. And then the derivative of the inside here. So it's either 1 over theta, or if it's 1 minus theta like this, it'd be like 1 over 1 minus theta times negative theta. So what's nice about this is that we can actually very quickly write this out, and that's what either is. So essentially what we do is like, well, it's either gonna be this guy or this guy. So depending on what probability is, you essentially just have to count up, and this is where the curriculum actually shows. It's like all you have to essentially do is you have to say how many times does heads happen times 1 over theta. And then you'd have like plus the probability or the number of times tails happens times 1 over theta minus 1. Okay. And so essentially with using those kind of values, like, oh, cool, like we don't have to really worry about this. This shouldn't be, sorry, I put theta here, this should be 1. Is that when you have these values, like, okay, cool, this is actually really easy now. Instead of having to do this huge, messy logarithm or derivative, we can simply just say the derivative is this guy right here without having to do anything. And this allows us to really quickly find out, like, hey, what are these values by putting in our values in here, solving for theta, and we have our theta MLE. So we don't have to like really do a whole lot of work. So that's kind of like why the motivation of why we're doing the log transform, or not log transform, we're taking the log of this function f of theta. So quick note though, is you'll see this argmax function here, this argmax function, okay? All this is really notation for is saying it's not an actual function. This function does not exist in the real world. There is no function called argmax. You can't put it on a calculator. You can't really put it in like a computer technically. So essentially what you're doing is you're like, hey, let me go ahead and say, you see this function g of x, or is this g of theta? This function g of theta, find where theta is the highest value. Basically, what is the maximum, what is the point of theta where it hits the maximum? Okay, basically like what is this point right here? And that's what this argmax is. But essentially all you have to do for doing this is you would take the second derivative and all this, or in this case, you can just simply find this and solve for the theta on here. So again, what's nice about this is like, okay, this is just a quick mathematician notation to say, hey, find the maximum argument, basically the argument of theta. Where is theta? Like what value of theta will give the maximum value? And since all we care about is that, we can basically do some fun tricks with like logarithms, so we don't have to actually do the full derivative of the real function. So I know there's a lot of like looking on this, like going back, you're like, oh, there's a whole lot of stuff going on here. But I wanted to give you guys a little quick like motivation of like what's going on compared to the curriculum. Like the curriculum actually walks through it, but one criticism or one kind of thing that I kept hearing back is like, why are we doing this? Like, I don't understand. What are we trying to find? And essentially it comes down to that we're trying to find, when is this function right here? What value of theta will be the maximum, okay, to make that likelihood happen? So basically like, is that, you can think of it like, is that coin fair or not? So if like, say, what's the maximum likelihood? It's like, well, there's basically like, it's likely to be fair or it's not likely to be fair. But we're trying to like, what is the maximum explanation of doing that? So it's a little subtle. There's quite a lot of like reading for that part. But I wanted to give you guys kind of a flow of like what that comes out to. So
if it was like a fair coin, would there just be, you know, many maximums for, you know, there would be, if it was a two-sided coin, would there just be two maximums?
it wouldn't necessarily be there be two maximums. It's that the maximum would say the parameter would give a 50-50 shot. So this is kind of abstract right now. Like it's tough for me to go through because it's kind of like, it's pretty technical. So let me just kind of show you, guide you guys to where this happens. So I can kind of show you really quickly. Because I didn't really talk about what theta is, but I don't even think the curriculum necessarily shows what that is. So I gotta load this, of course. But you can kind of think of it more like the theta is kind of like this abstract part of saying, is it, what thing would give it to be quote unquote fair? Or what is it likely that this coin is actually doing? So let's see how they change this a little bit. Okay, so you can kind of think of like determining the parameters that maximizes the possibility of this happening. So for example, if you have a coin that lands on heads 90% of the time, it probably means that your parameter means that the coin's actual true probability is a 90% probability. So that's kind of like the maximum likelihood. That's only with two parts. So I'm trying to do this explain without having to go really far into detail. And you can see here is that there's a lot of writing going through, but the main thing is like getting lost in the weeds. So like trying to say like, oh, like what this happens. And this theta 1, theta 2, basically you take this assumption, well, theta shouldn't change. So this is MLE assumptions. You can say, okay, theta shouldn't change given that these probabilities going through. And once you have that, essentially you can create this guy right here, which this theta is representing the theta MLE. Okay, and this is where I'm going to kind of skip through real quickly, so bear with me. But basically, you go through this part, you say, okay, well, we can take the derivative, we can take this part. It's a monotonically increasing function, so we can do the logarithm, right? This is showing why you can do this. And essentially, we can say, okay, well, we can do all this part. We basically just did the argument, the maximum argument of this function is the same thing as just doing the log, which is essentially just this guy right here. So essentially, okay, well, that means the derivative, we set this equal to 0. Okay, oh, there it is. Set it equal to 0 and say, okay, let's go and solve for theta. And that theta essentially simplifies down to this final form, basically saying how many heads over the total number of times that happens. So you can think of like theta being the true probability of getting heads, if that makes sense. And so our theta MLE is like what best explains getting this actual data. If your coin is actually fair, you would expect this happening. So it's kind of weird because, like, to be quite honest, if I gave you this first, that kind of makes sense. It's like, oh, what is the likelihood of this coin? Like, what's the actual probability of me getting heads on this coin? It's just how many heads did I get versus how many times I flipped it. That's what this summarizes to. But this is kind of going from the very beginning, saying, well, let's make it probability in a very generic, what's it called, like more abstract form with this thing called theta, and breaking it down, saying, okay, if we have the data going through and break it down to say what's the maximum likelihood of going through. What's nice about this, because it's super complicated versus like honestly, this is probably the easiest thing to just say. It's like, oh, well, it's just how many times you got heads versus tails. You can now generalize this to any probability space for multiple things. For example, a die throw or some other, probabilistic, sampling space essentially. And so this allows you to do this very quickly. And this generalizes to essentially anything you want. You could potentially have to just write down these parts right here, and you would have theta without having to go through the whole process of doing this part. So this is more or less a proof. So hopefully that kind of gives an idea. It's not an easy concept, if that makes sense. But I'd suggest read this through, try to follow just kind of reading it through and understanding like what's going on. For the record, you're not going to have to reproduce this yourself. Like, this is not something you're going to have to reproduce over and over unless you're really into that statistics, mathematics proof. But this is more like showing you the proof, saying, hey, this actually does happen and you can actually use this process. And the way I kind of see this with mathematics is like, we do mathematics to make things very general, so we can say something that you probably already know. So that way we can apply it to things that we don't know. So that's kind of like the idea here. I don't know if that necessarily answered part of your question, Eric. Okay. To be honest, if you still feel kind of confused, I wouldn't blame you too, because there's still a lot to go on here. Okay, cool. Any questions you guys have in general? Yeah. So cool. I was hoping like maybe
just trying to soak it all in,
It's a lot. Like I said, section 21 is not like a breeze. Oh, just gonna read this through and kind of do a little coding. It's a little more involved, which is why I'm kind of giving you guys the heads up. One last thing I'm just gonna mention is the maximum posterior. This is all on the GitHub right here, so you can kind of like do a summary. But basically, that's the next section after that maximum likelihood estimation. Basically saying, hey, what if we have a different posterior, basically? And it goes through, it's like, well, if you do that, you basically have this general form of this guy. But then it turns out, oh, wait, if you assume, if the prior, basically your prior knowledge is that the probability is uniform, then you essentially simplify this directly into MLE. So basically saying, hey, maximum a posterior or map estimation, it's the same thing as MLE when we consider the probability to be uniform. So it's just a kind of a quick side note, essentially saying, well, we can do this whole process again with a different kind of assumption, and we still arrive to essentially the same answer. But I just put this in there. Okay.